There are two kinds of waves that satisfy the wave equation. Waves in 3 dimensions that satisfy the wave equation can either be traveling waves or standing waves. So if the waves are traveling, then D'Alembert showed that a 3-dimensional standing wave has got a solution phi of r comma t, where phi satisfies the 3-dimensional wave equation, as some functional linear combination of a 3-dimensional wave number k vector dot r minus omega t plus another function that has got k dot r plus omega t, where omega satisfies the 3-dimensional wave relation. Omega is given by the ratio of the magnitudes of the speed to the wave number magnitude. Now these are called the forward traveling waves and these are called the backward traveling waves. So the traveling wave solution is that. Now what if you had no traveling waves but standing waves? So this is the traveling wave solution. And you can easily see that it satisfies this by putting it in that equation and verifying it, if that's one way of doing it, certainly. The standing wave solution is one where the waves don't appear to be moving forward or backwards, but they appear to form a steady pattern. For example, when you have a wave stretched between 2 points in a violin string and you're bowing it steadily, then it appears to be standing, not traveling anywhere. Even though if you microscopically examine it, it's moving back and forth with this propagation speed v. So we're interested in standing waves. So standing waves can be found by having the waves put in a certain confined space. So we'll look at a wave that can be packed into a box. So these boundary conditions are called box boundary conditions. So this is just like a generalization of the previous problem in 1 dimension to 3 dimensions. Let's take the box to be of dimensions L sub x, L sub y, and L sub z. The obvious boundary conditions are that at each of the faces the waves is going to be standing. So we follow the usual procedure of writing the wave phi, which is a function in general of x, y, z, and t, as a product of each of these functions. Substitute it in the wave equation and divide by x, y, z, t. When you do that, you're going to end up getting x double prime over x plus y double prime over y plus z double prime over z equals 1 over v squared t double prime over t. So this is just a generalization of the previous thing we had, where we just had x double prime over x equals 1 over v squared t double prime over t for the 1D case. This is just a 3-dimensional generalization of the 1D case. Now, how do we go from here? That's only a function of x. That's only a function of y. That's only a function of z. And that's only a function of t. I've written as proportional to, but really I mean function of. So what we're going to do is we're going to set each one equal to a constant. Now we can't set them all equal to the same constant, so these constants have to be different. So what we'll do is we'll set x double prime over x equal to some constant negative L squared. Now we are again going to eliminate a possibility of plus L squared because we don't want cosh or sinh. We want instead periodic, so we want sine and cosine. and L, M, and N are all going to be real. Similarly, y double prime over y is going to be negative m squared, and z double prime over z equals negative n squared. And then just because we've carried on like this, let's also do the same thing for t double prime. We'll say t double prime over t is negative gamma squared, because that also has to be a constant. These constants are not completely unrelated. They also have to satisfy that. So let's put them back in there. So I'm going to get negative L squared, negative m squared, negative n squared equal to negative gamma squared over v squared. So taking out the negative signs, I get L squared plus m squared plus n squared equals gamma squared over v squared. So that's the condition that governs these quantum numbers, as long as they're all real. So the box conditions demand that we only choose periodic boundary conditions and not Cinch and Cosh. So we are now going to have to quantize it. For quantization purposes, what we're going to do is we impose the box boundary conditions. X of 0 and x of Lx are both equal to 0. X of 0 will tell us that you don't have any cosine modes, and x of Lx equal to 0 means that we're going to get sine of, well, here you don't have k anymore. The wave number is not k, but in this case it's L. So sine of some quantum number nx times pi well, actually, let me do this more carefully. I'm going to have sines and cosines. Cosines are ruled out by that. So that tells us there's no cosine. The only other possibility is that I can have sine of Lx, but L times Lx equals to nx times pi. So that's what I get when I say that sine of Lx equals 0. L times Lx equals nx pi. So this tells me that L must be equal to nx pi over Lx. So my full solution is going to be sine of L times x, which is now indexed by a quantum number, so I'll get sine of nx pi over Lx. Well, similarly, I'm going to get sine of ny pi times x, y over ly, and sine of nz pi z over lz as the possible solutions by imposing the other boundary conditions. And the other boundary conditions are respectively y of 0 equals y of ly equals 0, and z of 0 equals z of lz equals 0. The first boundary condition will rule out the cosine modes. The second boundary condition will say the sine mode has to be equal to 0. And when you satisfy the sine mode equal to 0, you will end up with the quantization condition, just as I did here. So I'll remove some of these things here. So what I really did here was to set sine of L times Lx equal to 0, and that told me that L times Lx was nx times pi. So similarly, you get those other quantum numbers for these. So the full solution has got to be a product, or the of all these three things. Now remember, the time variable is still not written in stone, so we have that full freedom for the time variable. Now for the time variable, since the relationship between gamma and L, M, N are those, what we're going to do is write the full solution as follows. We'll write phi of x, y, z, comma t is going to be the sum over all these quantum numbers nx, ny, and nz going from 1 to infinity. So it's a triple infinity. I can probably write 3 sigma signs if you like. And then I have sine of nx pi x over lx times sine of ny pi y over ly and sine of nz pi z over lz, multiplying whatever the general solution is for the time variable. Now the time variable, again, you're going to get sines and cosines, but now the a's are going to be indexed by a triple where n vector is nx, ny, nz times cosine of gamma t plus b n vector sine of gamma t, with the understanding that gamma is not completely independent. Gamma is related to L, M, and N. So let's just, this is also gamma n, I should write, where because I had L squared plus M squared plus N squared equals gamma squared over V squared, we're going to write L squared, which is nx squared pi squared over lx squared plus ny squared pi squared over ly squared plus nz squared. This nz is not to be confused with n. Pi squared over lz squared equals gamma n vector. I think I should call this n vector because it depends on nx, ny, and nz, so it might be a good idea to call it n vector squared over v squared. So that's the relationship between these gammas and all these quantum numbers. If you want to think about it in quantum space, in the space of these integers, you have an integer lattice ellipsoid, of which this is the constraint equation. All right, now to find the constants a_n and b_n, you have to use some initial conditions. So one possibility is that I give you the initial shape of all these waves at time 0, and I also give you the initial velocity of all these waves, so the first derivative of this function at time 0. Then you can get a_n's and b_n's using the orthonormality of the three-dimensional Fourier series. So this is a 3D Fourier series, and if you carry out the orthonormalization of the 3D series, you're going to get the a_n coefficients to be 8 over lx, ly, lz, the integral from 0 to lx, integral from 0 to ly, integral from 0 to lz, the phi of x, y, z, 0, that's the first initial condition, the shape condition, and that's the initial velocity condition, times by the orthonormality of these Fourier series, lx, and then you have sine in the y and z similarly, dx, dy, dz. And the b_n's, to satisfy the b_n's, you'll have the same thing, except you'll take the first derivative. When you take the derivative, you're going to pull a gamma out. That gamma will end up in the denominator along with these things. So I'll call that gamma n, lx, ly, lz. And then pretty much you'll have the same triple integral, but now with this initial velocity condition, x, y, z, 0, and then all the signs again. nx pi x over lx times nx, ny pi y over ly times nz pi z over lz. I won't write all that. Dx, dy, dz. So this formally completes the complete solution of this, but for specific values of phi you can have different coefficients an and bn. So this is, again, the nature of these problems is that it's very methodical and very straightforward, but a lot of tedious work goes into them.